One day, the sun we trust so easily will begin to change in ways no human will ever see, and its earliest hints are already hidden in the quiet rhythm of its heartbeat. Tonight, on The Galaxy Scientist, we drift through the life cycle of a star like ours, how its warmth is built, how it slowly unravels, and how it ends as a pale ember floating through the dark. If this soft curiosity feels comforting, a gentle like and quiet subscribe help others find their way here. For now, settle in, and we'll follow the sun's distant horizon, unhurried and warm. Imagine a future so far away that no human memory could possibly reach it. A time beyond history, beyond language, when everything that ever reminded us of home has faded. In that distant age, the sun, our steady lantern, will grow restless in its old age. The sky that once brightened slowly with soft blue will seem to quiver, as if the air itself is holding its breath. A faint deepening of light on the horizon will swell into a blazing curtain, a wall of radiance spreading across the heavens. The gentle blue of morning will give way to something wilder, like an ocean of fire rolling overhead. Waves of heat will climb into the sky. Mountains that stood for ages, seas that cradled life, will surrender in flashes of unbearable warmth. Where night once wrapped the world in shadow, there will come a time when no shadow survives at all, only an endless, glaring day. This ending does not arrive in a single moment. Over millions of years, deep inside the sun, its core will slowly change and swell. Each sunrise, if anyone were left to see it, would mark a tiny step toward a harsher light. The calm golden disk will grow larger, redder, more swollen with time, until one day the horizon will no longer glow. It will burn. The serene line where sky meets earth will dissolve into flame. At last, the sun will stretch its fiery body outward, reaching beyond the path of Venus, and then beyond the orbit where Earth once circled. Solid rock will soften and flow like molten glass. Oceans will rise into steam, then vanish, boiled away into space. Any last tremor of breath, any final trace of life, will disappear beneath a shield of impenetrable fire. Gravity, the same gentle force that once held planets in a stable dance, will now draw what remains of our world inward, toward the vast wounded heart of an aging star. This is not a punishment, not a cruelty, but the quiet, inevitable destiny of a star like ours, and all the small worlds that cling to its light. In its final act, the sun will gather its inner planets to itself, not out of anger, but because it can no longer be what it once was. It is not a question of whether this will happen, only of when. For our solar system, the story of familiar skies, of blue seas and green continents, will end in that embrace of fire. To reach this ending, though, there was first a beginning. Long ago, about 4.5 billion years in the past, in a quiet arm of the Milky Way, there lay a cold, dark cloud. It was a giant molecular cloud, drifting slowly through space, still and shadowed. Its gas was mostly hydrogen and helium, the simplest of elements, mixed with fine grains of dust. That dust carried a richer story within it, the ashes of older suns. Long before our star existed, other stars had lived and died here, exploding as supernovae and scattering heavier elements like carbon, oxygen, and iron into the interstellar gloom. For ages, the cloud simply existed, heavy with possibility. Then, somewhere near its edge, or deep within its heart, the shockwave from a distant supernova passed through. Like a cosmic hand pressing into soft fabric, the wave squeezed and stirred the cloud. Gas that had drifted thin and loose began to gather into clumps. In some regions, the density grew just enough for gravity to take hold and refuse to let go. Those dense pockets of gas and dust started to collapse inward. As they shrank, they spun faster, like a dancer pulling in their arms. In one such collapsing clump, matter spiraled toward the center, and pressure built, squeezing the heart of that growing knot tighter and tighter. Deep inside, the temperature rose, climbing until the darkness lit from within. A young star was forming, but it was not yet the sun we know. Wrapped in layers of dust, it glowed softly in infrared light, like an ember hidden in ash. This was the protostar stage, the sun in its infancy. Around it, the leftover gas and dust did not simply fall straight in. Instead, it flattened into a wide, thin disk, swirling around the young star like a spinning halo. Material from this disk continued to rain inward, feeding the protostar and making it grow. From the star's poles, narrow jets of hot plasma burst outward, piercing the surrounding cloud and carving long, hollow cavities through the gas. In those moments, the hidden star was quietly reshaping its birthplace. Within a few million years, the core of this protostar heated to a critical point. Temperatures climbed to around 10 million degrees, hot enough that hydrogen nuclei could begin to fuse into helium. In that instant, something profound shifted. The inward pull of gravity that had been squeezing the star was met by a new outward push, the energy from nuclear fusion. The star's heart lit its thermonuclear engine, and the sun truly came alive. Once fusion settled into a steady rhythm, our star entered what astronomers call the main sequence, a long, calm middle age in a star's life. For billions of years, the sun would shine with nearly constant brightness, turning hydrogen into helium in its core and bathing the young solar system in light. The intense radiation from its surface swept away the thin leftover gas of the birth cloud, clearing the space around it. All that remained was the disk of dust and rocks and ice, where planets, moons, and smaller bodies would slowly gather and take shape. This was the quiet beginning of our star's life, born from the remains of older suns, gathered by gravity and kindled into a steady flame. It settled at the center of a newborn solar system, like a warm heart in a newly formed body. But the calm face we see when we look up is only a surface. To truly feel the story of how the sun will one day swell and consume its inner worlds, it helps to imagine what lies beneath that bright skin. At the very center of the sun rests the core, a dense, blazing furnace where temperatures reach roughly 27 million degrees Fahrenheit. Here, the pressure is so immense that hydrogen atoms are pressed together until they merge into helium, releasing bursts of energy in the process. Every tiny fraction of a second, unimaginable amounts of hydrogen are transformed, bit by bit, into new elements and pure energy. That energy is what becomes the sunlight that warms oceans, feeds forests, and paints the sky at dawn and dusk. The core stretches outward to about 1/4 of the sun's total radius, a compact heart compared to the whole. Beyond that central region, the heat and pressure slowly drop, and the core's direct power begins to fade. Surrounding it is a vast inner layer called the radiative zone, a deep, silent sea of hot plasma where energy tries to move outward in the form of light. But in this region, photons do not fly freely from the core to the surface in one smooth line. The plasma is so dense, so crowded, that each quantum of light is endlessly waylaid. A photon is emitted by one particle, travels a tiny distance, then is absorbed by another and sent off again in a new random direction. The journey becomes a chaotic, zigzagging walk, a slow dance through matter. Even though each photon always moves at the speed of light during its brief flight, its path is constantly interrupted. Because of this, the trek from the core's edge through the radiative zone is anything but quick. It can take a single photon on the order of 170,000 years to wander its way outward to the next layer. In this deep, opaque interior, energy does not rush. It seeps. It creeps outward, step by uncertain step, like a glow trying to find its way through thick fog. Farther from the center, something remarkable happens. Around 70% of the distance from the sun's core to its surface, the conditions change enough that the way energy is transported transforms completely. The temperature drops by a few million degrees, and the density of the plasma decreases sharply. At this point, radiation can no longer carry the load efficiently on its own. The plasma becomes more opaque to light because heavier ions can hold on to some of their electrons instead of staying fully stripped. Here begins the convective zone, a wide, restless outer shell about 125,000 miles thick. In this layer, heat moves not mainly through photons, but through motion. The plasma behaves like a vast, simmering ocean. Hot gas deep below becomes buoyant and rises in enormous, slow-moving plumes. As it rises, it carries energy toward the surface. When it reaches the cooler regions above, it sheds its heat and begins to sink again, making room for new hot material to rise from beneath. This churning cycle of rising and falling plasma acts like an enormous conveyor of warmth, bringing energy to the surface not in hundreds of thousands of years, but in weeks. The convective zone is full of giant cells, each one the size of a continent, slowly rolling and folding over on itself. If it were somehow possible to hover just beneath the sun's visible surface, the view would be strange and mesmerizing. A constantly shifting pattern of bright and dark patches, like a pot of gently boiling soup seen from very close, each bubble a plume of hot gas returning to space. When we look at the sun through powerful telescopes, we can actually see the tops of these convective cells. The surface appears grainy, sprinkled with tiny, shimmering tiles. Each of these granules is roughly 600 miles across. The brighter centers mark regions where hotter plasma is rising upward, while the darker edges outline areas where cooled material is sinking back down. Each individual granule lives for only a few minutes before dissolving and being replaced by a new one. Yet together, they cover the surface in a restless, flickering pattern. Beneath this rolling, bubbling skin, another subtle but crucial feature lies hidden. There is a thin, invisible boundary that marks the place where the calm, radiative interior hands off to the turbulent, convective exterior. This boundary is called the tachocline, a fragile-looking word for a powerful region. Here, the nature of the sun's rotation changes abruptly. Deep inside the radiative zone, the sun turns almost as if it were a solid ball, completing a rotation in about 27 days. But the convective zone above does not follow this rule. Near the equator, the outer layers rotate more quickly, taking roughly 24 days to spin once. Closer to the poles, they move more slowly, needing around 34 days. At the tachocline, located at about 7/10 of the sun's radius from its center, these different rotation speeds meet and clash. This mismatch creates intense shear, a stretching and twisting of the plasma as neighboring layers slide past one another at different rates. In this restless, electrically conductive material, charged particles are constantly in motion. The shifting flows generate electric currents, and those currents strengthen and tangle magnetic fields. Many scientists believe that within this narrow, hidden band, the sun's magnetic personality is forged. Here, deep under the glowing surface, loops of magnetism are wound up and amplified. Magnetic loops that will eventually reach out through the sun's atmosphere, shaping sunspots, flares, and the invisible threads of space weather that brush past our world. Deep inside that hidden boundary, the tachocline behaves like the sun's secret workshop. In this narrow, unseen band, magnetic field lines are twisted, stretched, and wound around each other by the shifting flows of plasma. That slow churning builds a global magnetic field that threads through the whole star, shaping its moods and its cycles. From this thin, invisible interface arise the quiet forces behind sunspots, bright flares, and storms of charged particles that one day wash over distant worlds. Following those magnetic threads upward through the restless convective layers, we arrive at the photosphere, the place our eyes know as the sun's surface. It looks like a solid, glowing disk, but it is really just a delicate skin of gas, only about 250 miles thick. Here, the plasma finally becomes thin enough that light is no longer trapped. Photons that have spent ages wandering through the interior are at last released into open space, rushing outward to bathe the solar system in warmth. The temperature in the photosphere sits at around 10,000 degrees Fahrenheit. Compared to the fury of the core, it is gentler, but still more than hot enough to make metal glow white. This is the layer where telescopes reveal a mottled pattern of fine structure, tiny, bright, and dark markings that hint at the turmoil below. Among them are sunspots, small, dark freckles against the blinding brightness, though many are larger than entire planets. Sunspots look dark only by contrast. They are cooler than their surroundings because intense magnetic fields have risen there from the depths. Those fields tangle and stiffen the plasma, slowing the boiling upflow of hot gas from below. With less heat arriving, the region cools and dims, becoming a shadowed island in a shining sea. Sunspots often gather in pairs or clusters, each group carrying opposite magnetic polarities, like the two ends of a loop of magnetic field that arcs up from within the sun and back down again. Some of these spots endure for days or weeks, changing slowly as the sun's surface flows carry them along. Around particularly active sunspots, the photosphere can glow even brighter. There, magnetic fields concentrate into regions called plages and faculae, subtle bright patches that raise the local brilliance just a little. At the same time, the whole photosphere is covered in those ever-shifting convection granules, each one a cell of hot plasma roughly the size of a large country, appearing, swelling, and dissolving in a matter of minutes. Taken together, they give the surface a soft, grainy texture, as if we were looking down on a gently simmering ocean of light. Above this glowing skin, the sun's atmosphere spreads into higher, more tenuous layers. First the chromosphere, then the corona. The chromosphere is a fragile shell only a few thousand miles thick, resting directly on top of the photosphere. Most of the time it is hidden, washed out by the sheer brightness of the lower layer. But during a total solar eclipse, when the moon covers the photosphere, the chromosphere reveals itself for a brief moment as a thin, ruby-red ribbon clinging to the sun's rim. Something strange happens here. Instead of cooling with height, the temperature in the chromosphere actually rises. Near its base, it is around 7,000 degrees Fahrenheit. Higher up, it can reach 14,000 degrees Fahrenheit or more. This upside-down temperature pattern is one of the sun's enduring puzzles. The chromosphere is ruled by magnetic fields, and it moves with a fierce, slender beauty. It boils with narrow jets of plasma called spicules, thin spikes of glowing gas that shoot upward like fleeting blades of fire. Each spicule is a geyser of solar material, lasting only a few minutes before fading. At any given moment, there may be around 10 million of them scattered across the sun, rising along the magnetic network. They can reach heights of roughly 3,000 to 6,000 miles and race upward at speeds of about 30 to 60 miles per second, flinging hot plasma toward the layers above. Many of these jets are thought to help feed and heat the outer atmosphere. Viewed through special filters, the chromosphere appears as a delicate, web-like pattern, where brighter threads trace the edges of larger convective cells called supergranules. Just above lies a paper-thin boundary known as the transition region, only a few hundred miles thick. Within this narrow band, temperatures leap from tens of thousands of degrees to nearly 1 million degrees. It is as though, in the span of a very short distance, the air around a campfire suddenly turned hotter than the flames themselves. Guided by invisible forces we are only beginning to understand. Beyond the transition region is the corona, the sun's outermost and most ethereal layer. Its name comes from the Latin word for crown, and that is exactly how it appears during a total eclipse. A pale, ghostly halo of light, fanning out from the hidden disk, with delicate streamers and plumes shaped by magnetic field lines. The corona stretches millions of miles into space, thinning as it goes, yet still bound to the sun's gravity and magnetism. In the corona, particles are so hot and energetic that they radiate mostly in X-rays and extreme ultraviolet light, invisible to human eyes without special instruments. Most astonishing of all, the corona is far hotter than the photosphere below, reaching those near million-degree temperatures despite being farther from the core's furnace. It is like stepping away from a fire and finding the air suddenly burning. This, too, is one of the great mysteries of solar physics, a riddle of how motion, magnetism, and waves conspire to deposit so much energy so far from the sun's heart. The corona has no sharp edge. Gradually, it thins into the solar wind, a ceaseless outflow of charged particles that streams away in all directions. This wind spreads throughout the solar system, wrapping every planet, every moon, every small, wandering rock in a tenuous bubble of solar influence. It carries with it the imprint of the sun's changing magnetic field, a quiet reminder that our star is not a fixed lamp, but a dynamic, breathing presence. To sense why the sun shines at all, it helps to imagine going back in thought to its core, to that hidden sphere of crushing density and searing heat. There, in the deep center, a process unfolds that might seem almost mystical if we did not know the physics behind it. The fusion of hydrogen into helium. It is a kind of nuclear alchemy, turning mass into light. In that hot, crowded heart, Einstein's famous relation, E equals mc squared, becomes a lived reality. A tiny portion of mass is transformed into energy, and that energy is what eventually becomes warmth on your skin and light in your window. The main path by which the sun accomplishes this is called the proton-proton chain, a sequence of reactions that quietly create the sunlight we see. The name may sound technical, but the idea is simple. Protons, the bare nuclei of hydrogen atoms, collide and combine to form helium. Step by step, picture two protons rushing through the turbulent chaos of the core. Each one carries a positive electric charge, so they naturally push each other away, the way like poles of two magnets resist being brought together. Classical physics says that, at the sun's core temperature, they should almost never get close enough for the strong nuclear force to grab them and fuse them into something new. Calculations based only on this classical view give a probability so small, it might as well be zero. By that reasoning, no fusion should happen, and the sun should be dark. And yet, the sun does shine. The resolution to this quiet contradiction lives in the subtle rules of quantum mechanics. Protons are not just tiny beads flying around. They also behave like waves, with their exact positions blurred into a soft, probabilistic haze. Because of this wave-like nature, they can sometimes do something that sounds impossible from a classical point of view. They can tunnel through barriers. Quantum tunneling allows a particle to slip through an energy wall it does not have enough energy to climb over. In the sun's core, that means that once in a great while, two protons can effectively appear on the other side of their mutual repulsion, close enough for the strong nuclear force to bind them together. The chance of this happening in any given encounter is unimaginably tiny, on the order of one successful fusion out of roughly 10 to the power of 28 attempted collisions. And yet, in the crowded furnace of the core, those rare successes happen often enough to keep a star shining. Deep in the core, every so often, it is as if quantum chance opens a secret door. Two protons that should have pushed each other away instead slip through the barrier and meet. When they do, something extraordinary happens. They merge into a single, slightly heavier nucleus, and the first step of the proton-proton chain quietly unfolds. In that first step, two protons fuse. One of them, under the influence of the weak nuclear force, changes its very identity and becomes a neutron. Together, the surviving proton and the newborn neutron form a deuterium nucleus, sometimes called heavy hydrogen. The reaction does not simply rearrange particles, it releases energy. A positron, the antimatter twin of an electron, flies off, along with an almost weightless particle known as a neutrino. The positron does not travel far. In the dense crush of the core, it quickly meets an ordinary electron. Matter and antimatter collide and vanish into pure light, releasing a flash of high-energy gamma radiation. The neutrino, by contrast, barely notices anything around it. It interacts so weakly with matter that it slips through the sun almost as if nothing were there, racing outward at nearly the speed of light. It carries away a small portion of energy, a quiet whisper from the heart of the fusion process. Right now, as you listen, unimaginable numbers of these ghostly particles are passing straight through you. Every second, billions upon billions of solar neutrinos stream through every square inch of Earth's surface, through rock, water, air, and bone, and almost none of them ever touch anything in a way we can feel. They are like messages from the core, passing right through our world and continuing into deep space. The deuterium nucleus, formed in that first step, does not wait long. Surrounded by a storm of particles, it soon encounters another proton. When the two collide and stick together, they create a nucleus of helium-3, a form of helium with two protons and one neutron. This second step also releases a burst of energy in the form of high-energy gamma-ray photons, adding to the growing sea of light in the core. Then comes the third stage. Two helium-3 nuclei, each with their two protons and one neutron, happen to meet. They fuse and rearrange, forming a helium-4 nucleus with 2 protons and 2 neutrons. The familiar helium that would fill a balloon, and they throw off 2 spare protons that are no longer needed. Those released protons drift back into the swarm and may, in time, begin the chain again with new partners. If we step back and look at the whole sequence, the picture becomes simple. 4 original protons, 4 bare hydrogen nuclei, have effectively combined to make 1 helium-4 nucleus. In the process, a small bit of mass has gone missing. The helium-4 nucleus weighs slightly less than the 4 protons that gave rise to it. That missing mass has been turned into energy, emerging as gamma-ray photons. It is this steady transformation of mass into energy that powers the sun, filling its core with high-energy light. On a page, the proton-proton chain can look like a tidy set of steps, a neat diagram in a textbook. In reality, it is playing out on an unimaginable scale. In the sun's core, roughly 4 times 10 to the 38th protons fuse into helium every second. Put into gentler words, hundreds of millions of tons of hydrogen are being converted into helium and energy, each heartbeat of a second. The power released by these reactions is staggering. The sun shines with a luminosity of about 4 times 10 to the 26 watts. A flood of energy comparable to billions of 1 megaton nuclear explosions going off every second, but spread out and softened into a steady, life-giving glow. For any one proton, though, fusion is still incredibly rare. Most protons spend their lives bouncing and colliding, billions of times each second, without ever managing to fuse. Yet the number of particles in the core is so immense that even a tiny fraction of successful encounters is enough to keep the sun burning steadily for billions of years. That is the quiet magic of large numbers. What is nearly impossible for one becomes inevitable for the collective. The high-energy gamma photons created in these fusion reactions begin a very long journey outward. At the moment of their birth, they hold the energy of sunlight in its youngest, most concentrated form, but they are born into a crowded, opaque environment. In the dense plasma of the core, a gamma-ray photon can travel only a tiny fraction of a millimeter before it is absorbed by an ion. That ion then emits another photon in a random new direction, perhaps with slightly less energy than before. This pattern repeats over and over, a kind of cosmic pinball game. A photon is absorbed, re-emitted, scattered, and absorbed again. With each interaction, its energy is gradually stepped down. With countless encounters, the original sharp gamma-ray photons are transformed into a vast swarm of lower energy light. First X-rays, then ultraviolet radiation, and eventually the visible and infrared light that our eyes and skin can sense. It takes on the order of hundreds of thousands of years for this energy, born in the heart of the sun, to wander outward through the radiative zone, then be carried by convection to the surface. Only when it reaches the photosphere is it finally free to travel in a straight line. From there, it crosses the emptiness of space in a single, clean sprint. Light leaving the sun's surface takes about 93 million miles in stride and reaches Earth in just about 8 minutes and 20 seconds. So the warmth on your skin at midday may have begun its journey when early humans were first teaching themselves to coax sparks into fire, or even long before that. The light that glows on leaves, shimmers on oceans, and seeps through your window is ancient by the time it arrives, yet feels immediate and new. For all its steadiness, though, the sun is not a perfectly calm lantern. Beneath its smooth golden face, magnetic fields twist and knot. From the photosphere up into the outer atmosphere, the sun is restless, capable of sudden, enormous outbursts. Long before telescopes, skywatchers noticed dark spots that would sometimes blemish the sun's disk. Ancient Chinese astronomers recorded these sunspots as signs in the sky, unaware they were seeing the visible marks of the sun's magnetic storms. In those regions, magnetic field lines punch through the photosphere like invisible ropes. They disrupt the normal convective flow that carries heat upward from the layers below. Where the field is strongest, the rising hot gas is suppressed, and the surface cools slightly compared to its surroundings. The magnetism there can be measured in thousands of units, known as Gauss, while Earth's magnetic field at its surface is only about 1/2 of a Gauss. The contrast is enormous, but we see it only as a slightly dark patch. Sunspots, as you might remember, often appear in groups, usually arranged in pairs with opposite polarities, like the north and south ends of a bar magnet laid side by side. Between these polarities, enormous magnetic loops arc up and away from the surface, forming grand curves that trap and guide searing hot plasma along their paths. These loops hang over the photosphere like glowing bridges, their feet anchored in the spots below. They do not last forever. As the sun's surface flows and deeper motions tug and twist them, stress builds within the magnetic structures. These loops and tangles become like strained muscles or wound-up springs. On the sun's face, they look like temporary scars, marking places where energy has been stored in invisible fields. And wherever energy is stored, it can also be released. Sometimes, in these magnetically complex regions, something sudden happens. Opposite magnetic polarities are pushed close together, and the field lines are forced into contact in ways they cannot easily maintain. When the configuration becomes too tangled, the magnetic pattern can abruptly rearrange itself into a simpler shape. This process, called magnetic reconnection, releases a tremendous amount of energy in a very short time. The result is a solar flare, a kind of stellar explosion that pours out light and particles across the spectrum, from radio waves to X-rays. It is as if a taut rubber band were twisted and stretched almost to breaking, then, in an instant, snapped into a new, relaxed form, letting go of all its stored tension at once. On the sun, that snap is not heard as a sound, but seen and felt as a sudden brilliance, a sharp release of energy in an instant. Solar flares erupt with a sudden ferocity, heating nearby material to temperatures of tens of millions of degrees in just minutes. X-rays and extreme ultraviolet light burst outward, followed by a wind of charged particles sweeping through space. The energy of a large flare is nearly beyond imagination, comparable to about 1 billion 1 megaton nuclear bombs detonating together, though from Earth we see it only as bright ribbons of light flaring along the chromosphere, each one tethered by loops of glowing plasma. Closely tied to these flares are coronal mass ejections, or CMS, vast clouds of magnetized plasma cast off from the corona. They often accompany flares, or the rising and breaking of solar filaments. Picture a great luminous arch high in the corona, becoming unstable, then tearing free and hurling billions of tons of sun stuff into the solar system. As these ejections expand, they can grow larger than the sun itself, even though the gas within is thin as mist. They race outward at tremendous speeds, sometimes between about 1,200 and 2,000 miles per second, far faster than the ordinary solar wind. When one of these immense clouds is aimed in our direction, it becomes a piece of space weather. 1 to 3 days later, it reaches Earth. In such moments, our star touches our world in ways both gentle and disruptive. When charged particles and magnetic shock waves strike Earth's magnetic field, they stir it into motion, triggering geomagnetic storms. The loveliest sign of such a storm is the aurora. In the north, the aurora borealis. In the south, the aurora australis. Energetic particles slide down the magnetic field lines and collide with atoms high in the atmosphere, causing the sky to glow in sheets of green, sometimes laced with reds, purples, or blues. They shimmer like silent curtains, reminders that the calm sky is woven into the sun's shifting moods. But stronger storms can do more than paint the night. Disturbances in the ionosphere can bend radio waves and scramble global positioning signals. Currents called geomagnetically induced currents can snake along power lines and pipelines, stressing equipment that was never meant to carry them. In March of 1989, such a storm filled the grid in Quebec with unwanted current, knocking out power and plunging millions into darkness for 12 hours, while auroras danced as far south as Florida. And long before that, the Carrington event of 1859 sent telegraph systems sparking and even ignited small fires, a warning from a time when electricity was still young. Today, with satellites, navigation systems, and global power networks, we are far more vulnerable. In the year 2012, a coronal mass ejection of Carrington scale swept through Earth's orbit, missing our planet by only a few days. Had it struck, the damage could have been profound: burned transformers, disabled satellites, widespread blackouts, a planet forced suddenly into quiet. Even milder storms can trouble the space above us. Heated atmospheric layers swell outward, thickening the air where low-orbit satellites travel. In February 2022, a modest disturbance caused dozens of newly launched satellites to encounter denser air than expected. They slowed, dropped, and burned up in the atmosphere. Astronauts, too, are vulnerable during such surges, especially those who may one day venture beyond Earth's magnetic shield to the Moon or Mars. For all these reasons, watching the sun has become a necessity. Its storms, though distant, thread themselves into our electrical systems, our communication networks, and the fragile machinery that orbits high above our heads. And yet, beneath the seeming randomness, a rhythm quietly pulses. Over centuries of observations, astronomers have discovered that the sun follows a cycle of rising and falling activity, something like seasons drawn in magnetic fields instead of weather. The most visible sign is the number of sunspots. During the active years, solar maximum sunspots bloom across the surface, sometimes hundreds, appearing over a few weeks. During the quieter years, solar minimum, the sun may appear almost smooth, its face unmarked for days or weeks. This roughly 11-year rhythm, first noted in the 1840s by Samuel Heinrich Schwabe, is now known as the Schwabe cycle. During the peak of the cycle, the sun is magnetically most restless, sending more flares and coronal mass ejections into space. Paradoxically, despite the abundance of dark sunspots, the sun shines slightly brighter overall. The light from surrounding bright magnetic regions, called faculae, outweighs the dimming from the spots themselves, making the star about 0.1% more luminous. At such times, the corona becomes livelier, streaming outward in elegant arcs, and auroras are more frequent, reaching farther from the poles. Beneath this activity lies the sun's magnetic dynamo. Roughly every 11 years, near solar maximum, the sun's magnetic field flips. North becomes south, and south becomes north. To return to its original orientation takes 2 cycles, making the full magnetic rhythm about 22 years long, known as the Hale cycle. Within each cycle, sunspots follow a graceful migration. They first appear at mid-latitudes, then drift slowly toward the equator as the cycle ages. This behavior, called Spörer's law, forms the shape of butterfly wings when charted over many decades. Yet the cycle is not a perfect metronome. Some cycles last about 9 years, others 14. Some are mild, others raw, and sometimes the sun falls into deep quiet. One such stillness occurred in the late 17th century, known as the Maunder minimum. For roughly 70 years, sunspots nearly vanished, and Earth entered a cooler era remembered as the Little Ice Age. Winters grew harsher, glaciers crept forward, and human history felt the distant heartbeat of a star whose rhythms reach across space and into our own unfolding story. After that long hush of the Maunder minimum, the sun we watch now feels almost exuberant. The current cycle, known as Solar Cycle 25, is blooming with a surprisingly high number of sunspots, hinting at a lively maximum for our world. In a society woven through with technology, this cycle acts like a rough clock for space weather risk. Around solar maximum, when spots and flares are more frequent, space agencies, power operators, and satellite teams quietly tighten their vigilance. Even the quieter years are not entirely gentle. During solar minimum, the sun's weakened wind offers less of a shield against the wider galaxy. More cosmic rays, high-energy particles born in distant supernovae, can slip deeper into the inner solar system. They pose extra risks to astronauts and to high-altitude flights, especially near the poles where Earth's magnetic protection is thinner. The sun's moods, both bright and subdued, shape not only light and warmth, but the invisible radiation around us. Beyond these internal rhythms lies an even slower, grander motion. Our solar system is not anchored in place. It drifts around the center of the Milky Way, circling in a vast orbit while gently bobbing up and down through the galactic disk. Stars are born, flare, and fade all around us. From time to time, another star passes relatively nearby. In cosmic language, nearby might mean a few light years away, and in rare cases, less than a single light year. Life on Earth might notice nothing at all in the short term, but in the deep outer regions, in the remote Oort cloud filled with icy comets, even that distant tug can matter. Left to themselves, the planets dance in a delicate gravitational balance that is mostly stable across the sun's long life. Their mutual pulls can introduce a whisper of chaos, and there is a tiny chance that, over billions of years, internal interactions alone could disturb the orbits of Mercury or Mars. Yet our system does not exist in isolation. It sits in a galaxy crowded with wandering stars, and given enough time, the odds of a truly close flyby steadily grow. To explore this, researchers have turned to simulations that stretch imagination and mathematics across vast spans of time. In a study published in the year 2025, scientists modeled the next 5 billion years of the solar system's evolution, not just with the familiar planetary interactions, but also with the gravitational nudges of passing stars. They ran thousands of versions of the future, varying the timing and masses of nearby stars according to what we know about the density of stars in our region of the galaxy. Those experiments suggest that earlier models, which treated the sun as alone in empty space, may have been too hopeful about long-term stability. Passing stars, even relatively small ones with only about a quarter of the sun's mass, can make a difference if they come within roughly 100 astronomical units, about twice the distance of Pluto's orbit. Their gravity delivers tiny kicks to planetary paths. Each nudge is small, But over time, such disturbances can build, tipping the system from graceful order into slow-growing chaos. In some simulations, the changes remain mild. Orbits stretch slightly, but the family stays together. In others, the consequences are more dramatic. The presence of random flybys increases the likelihood of planetary instability severalfold. A dwarf planet like Pluto, stable in models that ignore passing stars, now shows about a 5% chance of either being flung out of the solar system or colliding with another body over the next 5 billion years. Mercury, already the most vulnerable because of internal gravitational chaos, becomes even less secure. It's already tiny, less than 1% chance of eventually crashing into Venus or the Sun, climbs to about 1.8% when stellar perturbations are included. Mars, the quiet red wanderer, is not immune either. Simulations suggest around a 0.3% chance that it could be ejected or involved in a collision over the same time span. For Earth, the number is smaller still, yet not entirely comforting. Roughly, a 0.2% chance of being thrown into deep space or involved in a catastrophic encounter. A probability of about 1 in 500 across 5 billion years. On human timescales, that is practically impossible. On cosmic timescales, it is a small but real thread. Perhaps most striking is that when these instabilities are triggered by passing stars, they often do not take away just one world. Multiple planets can be lost, and the turmoil tends to begin earlier than in simulations where the sun is left alone. If a star were to pass very close within around 100 astronomical units, the calm clockwork of our planetary system could begin to unravel not 4 or 5 billion years from now, but within the next 1 or 2 billion. The distant Oort cloud would almost certainly be stirred, sending extra comets inward, and the neat circles of the planets could become tangled paths. The chance of such an encounter in the next 5 billion years, according to these models, is on the order of 5%. That is low enough that we need not live in fear, yet high enough to remind us that long-term stability is a gift, not a guarantee. Over those stretches of time, a single passing sun could whisper a different fate for our skies. While these distant possibilities hover in the background, the sun continues to surprise us in the present, on scales far smaller and more intimate. New instruments are peeling back layers of detail we never knew were there. In the search for deeper understanding, scientists have built the largest dedicated solar telescope in the world, the 13-foot Daniel K. Inouye Solar Telescope in Hawaii. With its wide mirror and sharp vision, it can resolve structures on the sun finer than we could ever see before. During its early observing campaigns around the year 2025, this telescope achieved something remarkable. It captured the sharpest view of the solar surface ever recorded. In those images, the familiar granules of the photosphere, those bubbling cells of hot plasma, were traced by something even more delicate. Ultrafine magnetic structures, only about 12 to 30 miles wide, appeared along the edges of the granules, like threads embroidered onto the borders of each convective cell. For scale, 12 miles is roughly the length of Manhattan Island, a size that feels immense on Earth, yet is minuscule against a star whose diameter is about 1 million miles. These tiny magnetic striations showed up as alternating bright and dark strands, rippling along granular walls. The research team suggests that they are caused by sheet-like curtains of magnetic field, pushing up through the photosphere where the rising and sinking plasma meet. What once seemed like a smooth, boiling pattern of light is now revealed to be laced with impossibly fine magnetic textures, subtle marks of forces at work beneath the surface. Along the edges of each solar granule, where hot plasma wells up and cooler gas sinks down beside it, something delicate takes shape. As the bright material rises in the center of a granule and descends along the neighboring lanes, the magnetic field is dragged and folded into tall, thin sheets. These become almost like vertical magnetic curtains, hanging along the borders between upflows and downflows. When light from below passes through these curtains, it is gently altered. Where the magnetic field is a little weaker, the light that reaches us appears slightly dimmer. Where the field is a little stronger, the light is slightly brighter. The result is a tiny barcode written along the granular edges, fine, bright, and dark stripes, tracing subtle changes in magnetic strength over distances of only a few dozen miles. It is, in a sense, a magnetic fingerprint stamped on the smallest scales we have ever directly seen on the Sunday. For years, high-resolution computer simulations hinted that such structures might exist, but they remained only suggestions on a screen. Now, with real images resolving features as narrow as 12 to 30 miles, those hints have become visible reality. These magnetic curtains are more than a curiosity. They may help control how heat and energy leak upward from the boiling photosphere into the higher layers, shaping the way the chromosphere and corona are heated. The fact that the sun's magnetism shows such fine structure suggests that the big mysteries might be built from countless small events. Tiny fluctuations in magnetic fields, appearing and disappearing like ripples on water, could add up over vast areas to warm the chromosphere, feed the corona, or even seed larger eruptions. The team studying these patterns has emphasized that understanding this intricate, small-scale magnetic architecture is essential if we hope to forecast space weather with more confidence. The grand flares and storms we see from Earth may begin with quiet rearrangements in these thin, unseen curtains of force. While we are learning to read these subtle patterns on the sun's face, our thoughts also drift forward in time. The star that sustains us now is changing very slowly, and one day it will enter a very different phase of its life. Even as we examine its present-day behavior in ever finer detail, another question hums in the background. What will become of our star when its fuel is gone? For the moment, the sun is in its long, steady middle age. It sits comfortably on what astronomers call the main sequence, quietly fusing hydrogen into helium in its core. Gravity pulls inward, the pressure of fusion pushes outward, and the balance between the two keeps the star stable. But as with every ordinary star, this balance cannot last forever. The supply of hydrogen in the core is not infinite. Roughly 5 billion years from now, the sun's central reservoir of hydrogen will be mostly spent, transformed into what is sometimes called helium ash. When that happens, hydrogen fusion in the very center will falter and stop. With the outward pressure from fusion dropping, gravity will begin to win. The core will start to contract under its own weight. As it shrinks, it heats up even more, the way air warms when it is compressed. Around that contracting helium core lies a shell of hydrogen that was once too cool to fuse. As the core heats, this shell becomes hot enough for hydrogen fusion to ignite there instead. Suddenly, the star has a new engine, a thin, burning shell surrounding an inert, shrinking center. Shell fusion actually releases more energy than the earlier, gentler core fusion did. The extra energy pushes outward on the layers above, causing the sun's outer regions to swell and expand. In this phase, our star will become what we call a red giant. The surface will balloon outward, while cooling enough that its light shifts toward redder colors. Over tens of millions of years, the sun's radius will grow by dozens and then hundreds of times. At its most extended, it may reach roughly 1 astronomical unit, the current average distance between Earth and the Sunday. In that swollen state, Mercury and Venus will almost certainly be swallowed by the sun's puffy outer layers. The fate of Earth is more finely balanced. Some models suggest our planet might just barely stay outside the sun's swollen edge, skimming the outer atmosphere of the red giant without being fully engulfed. Other calculations hint that drag from the star's extended gases and subtle changes in the orbit could slowly pull Earth inward, drawing it into a spiraling path that ends in vaporization. Whichever version turns out to be true, the outcome for life as we know it is much the same. Long before the sun's surface ever touches our world, its steadily increasing brightness will boil the oceans away, strip the atmosphere, and bake the planet until it is bare rock. Inside the red giant, the story continues. The helium core keeps contracting and heating until it reaches an astonishing threshold. When temperatures in the core climb to around 100 million degrees, helium fusion suddenly ignites. In a star like ours, this does not begin gradually. Instead, there is a brief, intense surge called the helium flash, a rapid onset of helium burning into carbon and oxygen. For a few moments, the core produces energy at a furious rate until its own expansion cools it and a new balance is found. After this, the sun will settle into a quieter phase again, this time burning helium in its core and hydrogen in a surrounding shell. It will be somewhat smaller and hotter at the surface, its color moving slightly toward the blue. This helium burning stage will last for around 100 million years, a shorter chapter compared to its long hydrogen-burning youth. Eventually, the helium in the core will also run low. Our star is not massive enough to light carbon fusion at its center, so when the helium is gone, the core will once more contract. The outer layers will respond by swelling again, even more dramatically than before. The sun will grow huge and unstable, entering its final giant stage. It will pulsate, expanding and contracting, while strong stellar winds carry material away. Over time, the sun may lose up to about 30% of its mass, blowing its outer layers into space. In its last throes as a giant, the star will shed those layers almost completely. What remains at the center will be the hot, exposed core, compressed into an object about the size of Earth and no longer sustained by fusion. This dense remnant is called a white dwarf, a glowing ember of a star, slowly cooling over billions of years. Around it, the cast-off gas from the outer layers will drift outward, forming a delicate shell or series of shells, illuminated by the fierce ultraviolet radiation from the hot core. This glowing envelope is what we call a planetary nebula, a name that lingers from a time when early observers mistook these round, hazy shapes for distant planets. In truth, they are the soft remains of dying stars, their outer atmospheres turned into luminous clouds. Our sun, too, will someday create such a nebula, sending forth veils of multicolored gas that expand into the surrounding interstellar medium over tens of thousands of years, mixing its material back into the galaxy. There is a quiet kind of beauty in this fate. We live now under the light of a star that is still in its long, stable prime, yet already carrying within it the seeds of its final transformation. It links us to the deep past and the far future all at once. The calcium in your bones, The iron in your blood, the oxygen you breathe, were forged long ago in the hearts of stars, not so different from our own, then scattered, gathered, and folded into this world. Every photon that turns leaves green, that glitters on the surface of the sea, that warms your face on a clear day began as energy in the sun's core, trapped for centuries before finally escaping. In that sense, we are truly children of the sun, built from stardust and sustained by its light. And as long as it continues to shine, there is room here on this small world for life to grow, to wonder, and to astonish.